Hello everybody, welcome back to the channel. So today's video is a little bit different than my normal kind of video. Normally I tackle math problems, but today we're going to be tackling a problem from physics, but it's actually really closely related to math because the way we derive the equation in physics requires knowledge on mathematical properties and using our mathematical tool set to try and model the problem that we're given. All right, so today we're going to be deriving an equation called time dilation. And what time dilation is it tells us that time actually moves slower if something is moving relative to you. If something's moving, time actually changes just by the fact that something is moving. And we're going to derive why this is true and explain why it's true just by using one fundamental postulate from physics that we're going to explain here. And then just from that, we're going to derive why this equation has to be true using mathematics and our common sense. All right, so first, I got to start by kind of explaining the physical dilemma that, or a physical property we observed that kind of went against our intuition. That is the idea that light, sorry, I paused for a second because I had a kind of spacey moment. I apologize. Light does not add velocities. We observed that this is a property that light does that goes against our intuition. Now you're probably asking, what does it mean to add velocities? Well, it's actually a concept that we're all pretty familiar with. It involves what happens to velocities if things are moving relative to you. So for example, let's say I'm standing on a dock, and here's me on the dock. All right, and I see a boat traveling past me, going at let's say 10 miles an hour. And let's say I have my friend or my twin brother standing on this boat, and he decides to throw a baseball off of it at 20 miles an hour. All right. So because he's on the boat, he's throwing it at 20 miles per hour, he's going to see it come out at 20 miles an hour. But because I'm standing on the boat is moving relative to me. So when he throws the baseball at 20 miles an hour, I'm going to see the baseball come out at 30 miles an hour because the boat is also moving at 10 miles an hour. So their speeds are going to add. So in summary, Ross will see the ball, or that's my twin brother, by the way. Ross will see the ball come out at 20 miles an hour, whereas I will see the ball traveling at 30 miles an hour. So if you ever heard the term that there is no absolute motion, this is exactly what it means. Velocity doesn't make sense unless we describe relative to what are we measuring velocity. Because relative to Ross, the ball is moving at 20 miles an hour, but relative to me, the ball is moving at 30 miles an hour. So when we describe velocity, we have to describe relative to what we are measuring that velocity. Otherwise, it doesn't make sense. There is no absolute velocity. There's only relative velocity and relative motion, as we have demonstrated here. All right. So this is a property that should match your intuition. It should make sense. If the boat's going at 10 miles an hour, I throw a ball off of it, then I should see it on the dock coming out at 30 miles an hour. And this is a property that works with all everyday things. But there's a problem, and that is when we start dealing with light, this property is no longer true. So we often denote the speed of light, which is about 300 million meters per second, as c, because it's easier to write c than it is to write this long number. Similarly to how we write pi, instead of writing 3.14159 all the way, etc. Instead of writing this number, we just write pi to describe this number. We do the same thing with c. We say c is the speed of light, and we just use c to describe the speed of light because it's easier to write than the actual number. All right, cool. So using the demonstration we did before, if we start using the same phenomenon or start trying to describe the same phenomenon, but instead we start dealing with light, we should expect something similar to happen. I should be on the dock. All right. Let's say that we have, it's a terrible drawing of a boat. All right, here's Ross. And let's say this time, instead of a baseball, he's a flashlight. All right, cool. So from the intuition we gathered earlier, right, when Ross shines the flashlight, he should see that come out. Let's say the boat's going at 20 miles an hour this time. All right. From the intuition we gathered before, Ross, when he shines the flashlight, he should see it come out at the speed of light, at c. All right, and that makes sense. And from our intuition from before, it would make sense that I would see the light coming out at 20 plus c miles per hour, because the Ross is shining the flashlight and it's coming out at the speed of light, but the boat is moving at 20 miles an hour. So I should see it as coming out as 20 plus whatever the speed of light is. That's what our intuition tells us. But the problem is we've done many physical experiments to try and demonstrate this fact, where we observe where we use machines or machinery to observe what the speed is from the person on the dock or the person who's not moving. And we use technology to observe what the speed of light would be for the person on the boat. And every single time our technology has told us that we don't get this result like we would expect, but we rather get that both people see it come out at the speed of light, which should go against our intuition. It should seem weird. If the boat's moving, why would I not see the light coming out as faster? It seems weird. But this is a fundamental truth that we have observed through experimentation. So we're going to have to deal with its consequences. Even though it goes against our intuition, we've shown that it's true with experiments. So we're going to have to deal with its consequences and see what happens as a result of it. So just from this one observation we made, we can do math to show that time has to change. Time travels differently for me and Ross, because we're both because Ross is moving and I'm not, or Ross is moving relative to me, I should say. And this one fundamental property we've observed, that the speed of light does not add velocities. You don't add the velocity of the boat to get whatever speed I'm seeing. It's always going to be the speed of light. Just this one fundamental fact has a lot of consequences to it, and we're going to derive those consequences using mathematics. So the layout for our derivation is going to involve imagining a thought experiment. So it's kind of similar to the boat example, except we're going to use trains and special relativity, which deals with the kind of math and science behind and the consequences of this observation of nature that light doesn't add velocities. That's the study of special relativity. We often use trains when we're doing thought experiments. I don't know why, we just do. All right. So we imagine a thought experiment. Here's the kind of setup to our problem. We imagine a thought experiment where we have a train going past a platform at a speed v, just some velocity v, whatever v is, we don't care. It's just going at some speed v. And I'm standing on the platform, and we have Ross standing in the train. All right. And the train has a certain setup. All right. The train has a setup where there's going to be a thing in the bottom, right? A photon emitter at the bottom. Remember, light behaves like a wave and a particle. In this example, we're going to imagine that it's behaving like a particle, because light exhibits both wave-like and particle-like properties. So in this example, I'm going to use the photon definition of light in our experiment, and it's fine because light is both those things. So we're going to imagine that as the train passes by me, Ross is going to press a button, and when that happens, a photon is going to launch from the bottom, bounce off of the mirror at the top, and come back down. All right? And we're going to see, we're going to do math to measure how long it takes for that to happen when Ross is looking at it. Like, let's say Ross had a stopwatch with extreme precision, and he measured exactly when he clicked the button, and exactly when the photon hit the floor again. We're going to measure the time it took for that to happen when he was watching it versus the time it took for that to happen when I'm watching it. And what will end up showing is that I observe it to have taken a different amount of time than Ross does, which is super weird, but it's one of the consequences of the property that we just outlined before. And we're going to show the math behind why that is true. All right. So the first thing we have to do is we have to break this up into individual scenarios. All right. We have to think about what is when this happens, what is Ross going to see and what am I going to see? So let's first think about what Ross is going to see. So Ross will be standing on the train. And this is a phenomenon you're probably all familiar with. When you're moving at a constant speed, when you're on an airplane, let's say you took an airplane and you shut all the blinds, you wouldn't really be able to tell you're moving, except for the fact that you're hearing everything. But you don't feel like you're moving. You don't fly to the back of the plane. You're standing. It feels like you're completely motionless. And if you look out the window, it feels like everything else is moving around you and you're standing still. That's what it feels like. So to Ross, it feels like he's just standing completely still and the platform is whizzing right past him. So as far as Ross is concerned, the platform is the thing that's moving, and he's the one that's actually staying still. But the bottom line is, Ross will feel like he's not moving. Similarly to how on an airplane, you feel like you're not moving when you're going at a constant speed. So what Ross is going to see is, let's say the height of the train is some distance L. Ross is going to see the photon go up and down. All right. So it's going to travel a distance of 2L, twice the length of the train. All right. And we know that velocity equals distance over time. So time equals distance over velocity. So then the time that it takes for Ross to see this event happen, for it to go up and down, is t equals the distance, 2L, divided by the speed that the particle was taking, which is the speed of light. So that's the time it takes for Ross to see the event happen. All right. And that's the simple thing. Ross's perspective is super easy. We can figure out how long it will take for Ross to observe this event to happen. All right. The next step is a little harder. We have to figure out a mathematical way to describe how long it's going to take for me to see the event happen. And we're going to see if we get the same thing. If we get different things, that means that time has to be traveling differently for Ross than it is for me. So let's look at the example from my perspective. All right. So you can imagine that when Ross presses the button, the train is going to be in a definitive location. But once the light reaches the top, the train is going to have moved forward a little bit because the train is moving. So once the light hits the top, the top mirror is going to have moved forward a tiny bit. Then once it travels back down, the train is going to have moved a little bit further as well because it's moving. So when it travels back down, then it's going to hit the bottom somewhere over here. Because the bottom will have moved as the train moves as our experiment goes on. And when we shine a light, it's going to take time for the light to reach the top and the bottom. So in that time, the train has moved. So when it goes back to the bottom is going to be over here. So I view the path of light as looking something like this, as going up here and then up down here, traveling at a diagonal path. That's because the train is moving relative to me. So when I see the light go up and hit the top, it's going to be traveling diagonally because the top is going to move. So if it's going to travel up and hit the top, it has to travel diagonally in order to hit the top. So this is how I'm going to see the light move. I'm going to see it move differently than Ross did. Ross is on the train, so he's just going to see it go up and down. I'm seeing the train move, so when the light goes and hits the top, I'm going to see the light has gone forward a little bit because the top has also gone forward a little bit. And the reason is it wouldn't make physical sense for Ross to have seen it hit the top and for me to have not seen it hit the top. If you're confused about why light travels diagonally when we launched it upwards, it's due to a physical concept that I'll explain very quickly. It's the idea that reality has to be conserved. Like I can't see something happen and Ross can't not see that thing happen. Let's say Ross put a detector on the mirror on the top, and that detector, if it was hit by a light beam, would make the train explode. All right. If that were the case, and I saw the light go directly up, then to me it would look like the light is not hitting the mirror at the top. Because if I saw the light going directly up, like you would expect it to, then it won't hit the mirror. So if there was a detector there that would make the train blow up, then Ross would see it go right up, hit the mirror, and then the train would explode. So Ross would see the train explode. But if I saw it go directly up, then it would not hit the detector, and I would see the train not explode. So Ross sees the train explode, but I don't. So reality is not conserved. That should hopefully sound crazy, and it is. And physicists realize that can't be the case. So I'm going to have to see the light travel diagonally in order to hit the mirror at the top because reality has to be conserved. Ross can't see it hit the mirror at the top, and Ross can't see it hit the mirror at the top and have me see something else. We have to see the same thing. So that's why the light is traveling diagonally to hit the mirror at the top, because the mirror is moving, and I also have to see the light hit the mirror at the top, or else reality won't be conserved. So this is the path that the light travels from my point of view. And we're going to try and extrapolate some information. Let's say the entire time that it takes for the light to travel from up and down is t prime. We're going to label t prime. So we have a different notation from the t we used earlier, right? That means that the first distance is going to take half the amount of time it takes to travel the whole way. So let's say it takes t prime seconds or whatever amount of time to travel up and down. That means the time it takes to travel halfway is t prime over 2. It's taking half the amount of time to travel up to the top. So we know that it's traveling at a speed of c. Geez, that was a terrible voice crack. So distance equals, is it time? I forget. So velocity equals distance over time. Distance equals velocity times time. All right. So the distance of this path is going to be c times t prime over 2. Because we're taking distance equals velocity times time. The time it takes for the light to travel this path, as we said, is t prime over 2. And the speed it's going is c. So the distance of this path is c t prime over 2. We can use the same logic to show that this path also has a length of c t prime over 2. Same as before, we're going to see the train have the same vertical length because we have to see the same thing pretty much. Or at least in the vertical direction, we have to see the same thing. If you Google length contraction, there's a whole other can of worms. But anyways, we're going to see the height of the train be the same that Ross did. So the height of the train is going to be L, like Ross saw it. Now the only thing is to figure out what this vertical distance is going to be. Because we can figure out what this distance is going to be, we're going to have a right triangle. And we can find a way to relate all of these sides. Well, notice that the train is moving in between these 2 points. The reason we get this distance is because the train moves. So the mirror was originally up here, but by the time the light gets up here, the mirror has moved over here. So this distance is going to be however far the mirror moved during that time interval, during the time it took for the light to get up. All right. And if the train is traveling at a velocity of v, then the mirror has moved at distance equals velocity times time. So the distance the mirror has moved is vt prime over 2, because the time it takes for the light to get to the top is t prime over 2. So the distance the mirror has traveled is vt prime over 2, where v is the speed of the train. So this distance is vt prime over 2. And now we can use the Pythagorean theorem to relate the things together. We see we have a leg here, and a hypotenuse here. We can relate them with the Pythagorean theorem by saying vt prime over 2 squared plus L squared equals ct prime squared over 2, or ct prime over 2 squared, just from the Pythagorean theorem. All right, I'm going to subtract this from both sides. I'll get L squared equals ct prime over 2 squared minus vt prime over 2 squared. All right, I'm going to expand this using our exponent rules. If I take a fraction and square it, it's squaring the top and the bottom. So I'm just going to simplify this using some algebra. We're going to get L squared equals c squared t prime squared over 4, because that's 2 squared, minus v squared t prime squared over 4. All right, and we can combine these into one fraction because they have a common denominator. So I'm just going to do that very quickly. I can combine these two fractions to give me this over 4. And you'll notice the terms on the top, they share a t prime squared. So I can factor out the top to get this all equals to, this is equal to t prime squared times c squared minus v squared over 4. All right. And I'm trying to solve for t prime here. I'm trying to figure out how much time did I observe to have passed. So let's go back. Let's go to another slide and illustrate what we have so far. We have that L squared equals t prime squared times c squared minus v squared over 4 from the algebra we did. So if I want to solve for t prime squared, I can multiply both sides by 4. 4L squared equals t prime squared times c squared minus v squared. So dividing both sides by c squared minus v squared, I'm going to get 4L squared equals, 4L squared over c squared minus v squared equals t prime squared. So now if I want to find what t prime is, you can say t prime is equal to the square root of 4L squared over c squared minus v squared. All right, cool. So when we take the square root of a fraction, we can take the square root of the top and the square root of the bottom. So when we do that, we'll notice the top is a perfect square. So using some algebra, we'll get that t prime equals 2L over c squared, or over the square root of c squared minus v squared. All right, and here's our answer. But the issue is, if you remember from before, we said that Ross saw time to have traveled at this distance. Ross saw time to have passed by this much, 2L over c. So I saw time to have traveled a different amount, as we've just shown. So I want to try and find an equation that relates the amount of time that I saw to have passed to the amount of time that Ross saw to have passed. And to do that, I can manipulate this equation. All right. If t equals 2L over c, then tc over 2 equals L from some algebra. So I can go back to my equation on all the way over here, and I can replace L with what we said it was equal to in the previous in Ross's example. So then t prime equals 2 times tc over 2, all right, over the square root of c squared minus v squared. Let's go back to the slide and see what we have. So we have t prime equals what was it? 2 times tc over 2 over c squared minus v squared, the square root of c squared minus v squared. Cool. So we have a 2 up top and a 2 on the bottom here, so they cancel. So we're left with t prime equals tc over the square root of c squared minus v squared. So we have a c up top and we have a c on the bottom, and we want to try and find a way we can manipulate it algebraically to get some cancellation here. So I'm going to rewrite the bottom as this. The square root of c squared minus v squared is the square root of c squared times 1 minus v squared over c squared. Because when you distribute the c squared again, you'll get the same thing we get over here. The square root of a product is equal to the product of their square roots. So this square root is going to be equal to the square root of c squared times the square root of 1 minus v squared over c squared. The square root of c squared is just c, so we can rewrite this entire fraction as t prime equals tc over c times the square root of 1 minus v squared over c squared. The c's end up canceling, and we get our final equation for time dilation. And if you Google time dilation, this is the equation you're going to get, all right? And it relates the amount of time that has passed between two people that are traveling relative to each other, all right? So t prime, remember, represents the time I saw to have passed, and t represents the time that Ross saw to have passed. And this relates the two times we've seen to have passed. And notice how they're different. If they were the same, we should have gotten t prime equals t. If we had found that t prime equals t, we would have figured out that time travels the same for both of us. But instead, we found out that time travels differently from both of us as given by this equation. And you can see they're related by this equation. The amount of time that I saw to have passed is the amount of time that Ross saw to have passed divided by the square root of 1 minus the speed of the train squared divided by the speed of light squared. So this equation relates the amount of time it takes for someone to observe something happening relative to someone else who's moving relative to them. So it relates the amount of time that two people moving together will have seen it take for an event to have happened. So this is time dilation. And it's a really cool equation because it tells us that time is not absolute, but rather relative. There is no universal clock. There is no universal clock, all right? What that means is there's no absolute time. The time is not traveling or passing at the same rate for everyone. Time is relative, and it depends on whether you are moving relative to someone else, as we have demonstrated with our thought experiment and our math, as a consequence of the fact that light does not add velocities. Just from that observable consequence that we saw, we can see that time has to travel differently for people moving relative against each other. Otherwise, just from the fact that light travels the same for both of them. We derived that with a thought experiment and showed the math for it. So hopefully that makes 100% sense, even though it might seem a little weird that time would travel differently for people moving relative to each other. Hopefully the math at least convinces you that it's true. So the consequences are time is not absolute, and time depends on whether you are moving relative to someone else. But then you might be asking, well, why do we not observe this phenomenon in real life? When I'm running, why do I not see time traveling slower for me than it is for someone else, or vice versa? And the reason is because we have to look at this equation, right? C squared is 300 million squared. That's a huge number. So when we're traveling, when we have velocities, right? The velocities we deal with are usually super small. Like when I'm running, I'm traveling like what? I want to say like 5 meters per second. I have no idea how fast I'm traveling. 5 meters per second squared is super small compared to 300 million squared. So this fraction is going to be basically zero, indistinguishable from zero. So we're going to get basically t prime equals t over the square root of 1 minus 0, which is t prime over t. T prime equals t over the square root of 1. So then t prime equals t over 1, and then t prime equals t. So in everyday phenomenon, because our velocities are usually super small, we observe t prime to be equal to t. Because in everyday phenomenon and velocities, this equation tells us that the times we get will be basically indistinguishable from each other, because velocity is so incomparably small, to the c squared term on the bottom. But it also does tell us that if we start going faster, a comparable fraction of the speed of light, then time will get more and more wonky. Additionally, this equation also tells us that we cannot exceed or go at the speed of light. Because if we went at the speed of light, then we get 1 minus c squared over c squared, which is 1 minus 1. Then we get 0. So we get t over 0. So we get an undefined time. So it tells us that we cannot achieve, we can never be as fast as the speed of light, because then time will not make sense. Additionally, we can't go faster than the speed of light, because then we'll get 1 minus a number bigger than 1, which will give us a negative number in the square root, which will give us imaginary time, which doesn't make sense. So time dilation not only shows us that time is relative, but also shows us why we can't go faster than the speed of light. And it also shows us that the effects of time dilation increase and get more wonky the faster we go. So that's time dilation. Hopefully it fostered your curiosity for learning a little bit about special relativity. I encourage you to watch videos on length contraction, which is another consequence of the phenomenon we observed that light does not have velocities. And it's super wonky, but hopefully the math that is outlined in those videos and the math outlined in this videos will convince you that this is a true phenomenon and not just fairyland physics. It is a true phenomenon, and we have demonstrated why it is mathematically from our observations and from simple math, the Pythagorean theorem, etc. So thank you for watching the video. I hope you had a good time. I hope you understand time dilation, and I hope you leave this video understanding the universe a little bit more than you did coming in. So that's all for today. Thanks for watching, and I'll see you guys in another video.